Okay, my name is Eric Murphy, and in this talk I will be discussing science that has currently been imagined that could be achieved with a next generation very large array, the topic of this special session. So quickly, you'll have more technical talks coming up, but I thought I'd give a quick picture as to what the next generation VLA looks like. It is a new facility, not just an upgrade to the very large array, but it adds, a completely new telescope with a new scientific frontier in mind, and that frontier is thermal imaging at milli-arcsecond resolution. And this is not anything new. This was a scientific area that has been looked at before, back when they were performing the upgrade to the very large array, the EVLA, and actually part of the phase 2 project to achieve the science. But at the time it was realized that to really get at this science successfully, you need such an increase in sensitivity and angular resolution that with a modest upgrade to the facility it just wouldn't be achievable. So not surprisingly, the sensitivity and resolution goal of the next generation VLA is an order of magnitude both increase in sensitivity and angular resolution of the VLA and ALMA. The frequency range covers 1.2 to 116 gigahertz. That goes right from H1, atomic gas tracer, all the way to CO, fundamental transition, J equals 1 to 0 at 115 gigahertz, a key diagnostic of molecular gas in the universe. The telescope is to be located in the southwest, leveraging existing infrastructure right now where the VLA is located, and spread out through the U.S. Southwest, in New Mexico, Texas, and Arizona, and down into Mexico for a good north-south baseline to achieve some of the key science. It is currently considered largely low technical risk. There's nothing new that we would have to wait to develop in computing or materials that wouldn't allow us to build it right now. Of course, during our design and development phase, we're looking for areas where improvements can be made to cut costs, and new materials that are on the horizon can be used in computing expectations as well. So the next generation VLA, here's an overview of what the distribution of antennas will look like on the top left. As I already said, the frequency coverage goes from 1.2 to 116 gigahertz. It consists of a main array of 214 18 millimeter offset Gregorian antennas. All the antennas have fixed locations across the southwest. There is also a short baseline array of 19 6-meter offset Gregorian antennas that are used for short spacings, as well as using for the 18-meter antennas in total power mode to fill in the UV hole even left by the short spacing rate. So, providing sensitivity to essentially all angular scales. And then there is the long baseline array component, which is an additional 30 18-meter antennas spread across the continent to enable very long baseline interferometry. And the receiver configuration is on the right, where we cover the 1.2 to 116 gigahertz in 6 receivers located in 2 dewars. And here's just another slide showing the distribution of antennas. So we have a very centrally concentrated core of antennas, and that's to enable some of the key science that requires low surface brightness imaging, as you'll see shortly. Nearly half of the collecting area is located within this central kilometer. And then when you expand out to about 36 kilometers, which is the footprint of the existing VLA, that's roughly 80% of the antennas. And then there's another roughly 20% antennas extending out to 1,000 kilometers. And then, of course, the antenna locations for the long baseline array, which are antenna stations, so multiple antennas at each of the locations for paired calibration and increased sensitivity. So the description of the array that I just presented is solely based on the level 0 science requirements that come from these NGVLA key science goals. And this is what was put together by our science advisory committee, working along with the community, a number of science working groups, and they prioritized, they set out to obtain a large number of science use cases from the community, and then through a prioritization process came up with these 5 key science goals. So, and I'll go through them. First is unveiling the formation of solar system analogs on terrestrial scales. probing the initial conditions for planetary systems and life with astrochemistry, charting the assembly, structure, and evolution of galaxies over cosmic time, using pulsars in the galactic center as fundamental tests of gravity, and understanding the formation and evolution of stellar and supermassive black holes in the era of multi-messenger astronomy. So, as you can see, that is a very broad scientific portfolio. Because of that, it is naturally highly synergistic with many other facilities that are on the horizon or on similar timescales. And here I list a number of things, a number of facilities that may or may not be come online, but just to show where the NGVLA fits into some of their key science, or where they're specifically optimized for science cases. So, for example, I'll go into a little bit more detail on this because I'm sure there's interest, is the SKA, and then also I have their LINX, which is one of the proposed flagship X-ray missions for NASA. And those observations from those facilities are really focused on looking at the atomic and non-thermal component of the universe, whereas the NGVLA is really looking at the molecular gas in the universe and thermal emission. Similarly, ALMA is really by observing in the submillimeter and terahertz regime is tracing warm star-forming regions in galaxies, while the NGVLA accesses the cold, dense fuel for star formation. LUVAR-HABEX, another couple possible NASA flagship missions. But one of their key science goals is imaging Earth-like planets after they formed. And as you'll see, the NGVLA is looking to image the terrestrial zone of planets as they are forming. So for a complete picture of planet formation, you really need both facilities to get at all of the physics that's going on and ultimately seeing what the end product is. And I'll just leave it there, and folks can look at the slides on their own. So also, I want to point out that the NGVLA really does bridge the wavelength coverage that is that the SK will provide, as well as what ALMA is providing now. It really bridges that gap and enables a different set of science. So highly complementary to these facilities. In the left panel, you see a plot of effective collecting area over system temperature or sensitivity as a function of frequency, and you can see that the NGVLA really straddles right in between the low frequency megahertz regime, where the SK will be magnificent, as well as before the ALMA turning up as you hit the terahertz regime, which is inaccessible, of course, except from high sites like where ALMA is located in Chile. The plot on the right shows angular resolution against wavelength for both facilities of all wavelengths. And what I want to highlight here is that horizontal line shows the angular resolution necessary to achieve 1 AU linear scale resolution at a distance of 140 parsecs, the nearest major star-forming region, and that is for studying forming Earth-like planets. And not surprisingly, you can see the US ELTs over there on the right are approaching that sort of angular resolution as well, because some of their key science is to, again, image and characterize atmospheres, actually, of terrestrial planets that have formed. So, with the NGVLA, in addition to ALMA's SK, it really seems to me that it's building this global suite of radio through submillimeter interferometers that will be an extremely powerful tool set for the community. Now, focusing a little more on the SK and NGVLA, again, because I assume there's some interest here, I just want to show how complementary these two facilities really are. So right here I'm showing the SK high priority science objectives on the left, and on the right here, these are the NGVLA key science goals. And you can see that there is definitely overlap in some of them: cradle of life and planet formation, pulsars, H1, but a majority of the science cases are kind of distinct. And while maybe in a broad sense you could argue that a lot of the science overlaps, the way that the facilities attack and try to get information on these science areas is fundamentally different. And I'll show that here. So again, these are showing the SK high priority science goals, as well as the NGVLA key science goals on the right. And the relative size of these colored blobs that where they have the names of the key high science priorities or key science schools on them, is reflective of how much survey area that is necessary to achieve those goals. So you can see on the left, if you were to execute the entire SK high science, key science projects, you'd need to image roughly 90 square degrees of area on the sky. Whereas on the right, to execute the NGVLA key science goals with their planet formation surveys, etc., you only need to image roughly 40 square degrees. So that's almost more than 3 orders of magnitude in area that needs to be imaged with the SK for those science goals relative to the NGVLA. And of course, that's okay because the facilities are being built to optimize for that. The SK is being built to enable large area surveys, or large area mappings, where the NGVLA really is geared towards more detailed follow-up, going very deep on a very narrow piece of area on the sky. And this is where the complementarity is, because when the SK will undoubtedly going deep and covering large parts of the sky, uncover new populations of sources, and the NGVLA will be sitting there at the same time, ready to go up and go on and observe and characterize these new populations of sources. So it's very exciting. As I'm going on, I just want to say, so far we've had very strong community participation in the NGVLA effort, both with the science case and community science studies, etc. So this is just a montage of all of the universities that have been involved so far, as well as industry partners, well, not necessarily partners, but industry folks, and international communities that have participated significantly so far. And I'm sure I'm missing some of the folks, and this should be updated soon. Another point I really want to make out is showing what our community looks like. And it's, these are images or pictures of 2 recent science meetings, one in 2018, one in 2019. And there are just a lot of young faces there. Roughly half of the folks at each of these have been early career astronomers, and a third students, which is incredibly impressive. And furthermore, we actually had our first internationally led science meeting at NAOJ last September, and roughly 100 participants there. And again, maybe not surprisingly, I don't know, the majority of folks there were early career with a large amount of students. Okay, so far to date we have a ton of science material that has been published. We have our science book, so I suggest folks go look at that if they want any more detailed information on the broad range of science that the NGVLA can accomplish. We've also submitted many white papers to the ASHRAE 2020 Decadal Survey. Those are available on ADS. We also have our project paper that was submitted to ASHRAE 2020 available on ADS. The NGVLA reference design concept is completed and available online. And we've been interacting with ASHRAE 2020 in terms of presentations as well. Okay. So roughly, quickly going through the NGVLA key science goals. The first one is unveiling the formation of solar system analogs. The NGVLA will measure the planet IMF down to 5 to 10 Earth masses and unveil the formation of planetary systems similar to our own solar system. On the left here, you see an image of ALMA at 1 millimeter, where the basically you need to really get into that central obscured region to see where all the action's happening on terrestrial scales. So the blow up there is a simulation of what the NGVLA could do at 1 centimeter for a solar system similar to our own, having Saturn, Uranus, Jupiter, and Neptune mass planets. And the central figure basically shows the planet semi-major axis plotted against planet mass and Earth masses, and shows that how the NGVLA will approach, or they have the ability to detect Earth mass, single Earth mass planets. And how much parameter space is opened up by the NGVLA, given what is known about planets or extrasolar planets relative to ALMA, the ELTs, and other facilities. And just to push on this further, I think this is one of the most remarkable things, is that by observing these protoplanetary disks on sort of a monthly cadence, the NGVLA will effectively turn planet formation science into a time domain science by being able to measure the orbital motions of planets and related features on some of these time scales. This is, I feel like, just an unbelievable, a transformative achievement. All right, our second key science goal. This shows the a synthetic, a modeled spectrum of 3 complex organic molecules that are not currently detected in the ISM, but which are good candidates for detection. And this just shows that the NGVLA will be able, given in a 10-hour observation, be able to dig up some of these prebiotics if they exist. Of course, we don't know what the structure is, but it will be routine in this frequency range for the NGVLA. The NGVLA will work to chart the assembly and structure evolution of galaxies from the first billion years. The first plot up top shows a simulated SMG, submillimeter galaxy at a redshift of 4.4 with a star formation rate of 400 solar masses per year. And the 3 panels basically show what the galaxy would look like in CO 4 to 3, so a higher excitation CO line, which is really looking at warm gas, and not surprisingly, when you look at the simulated observation, it's really centrally concentrated because that's where all the action is for star formation. The central image shows an NGVLA simulation for CO2 to 1, and then the right image shows the NGVLA image for CO1 to 0. So comparing the left and the right panels, there's a qualitative difference in the imaging. If you wanted to know what the total molecular gas content of this source was, you really need to go to the low J lines with the NGVLA. It would be virtually impossible to determine what the total molecular gas content is by trying to correct this ALMA CO4 to 3 image. And in doing so, at the bottom you'll see what the NGVLA will be able to do by increasing the precision on which we can understand the cold molecular gas content through cosmic time. Key science goal 4. So the plot here on the right shows the currently known pulsars in the galactic center. Of course, finding pulsars in the galactic center is exciting and important because it will enable new tests and theories of gravity, constraints on exotic binaries, star formation histories, etc. So while there are only a handful, half a dozen pulsars known in the galactic center, estimates based on the star formation properties in the galactic center suggest that there should be thousands of pulsars, up to 1,000 pulsars, but we don't detect them. So why is this? The thought is that the searches so far have been done at low frequencies, and radio wave scattering towards the inner galaxy really decreases the sensitivity of such searches. So by being extremely sensitive at higher frequencies, the hope is that the NGVLA will be able to uncover these pulsars that have so far eluded us. And of course, if we don't detect them, that might tell us actually something fundamental about star formation and the IMF in the galactic center. The last key science goal here is understanding the formation and evolution of black holes in the era of multi-messenger astronomy. So first, unaffected by dust, NGVLA sensitivity and angular resolution will be able to really resolve dual AGN and black hole binaries and measure proper motions over 5-year periods. This is shown in the right here hand panel figure of the projected nuclear separation as a function of redshift. And again, that orange area shows where the NGVLA will have enough sensitivity and angular resolution to measure the orbital motion or expansions of merging, exploding supermassive black holes, and trigger gravitational wave events. Additionally, the NGVLA, unaffected by dust obscuration, will be able to pick out black holes of all masses in the galaxy through follow-up of pre-selection from other wavelengths to determine, using proper motion, to see if the black holes are actually in the galaxy. Before concluding, I just want to highlight or let people know that while COVID-19 has made it so we do not have a live science meeting this fall, we are going through and having our in-person meeting, which is on compact objects and energetic phenomena in the multi-messenger era in St. Paul, Minnesota. The plan, if everything goes well, will be to have this meeting next June. But in lieu of having our live meeting this year, we are organizing a virtual 2-day, 2-hour mini conference where all of the invited speakers have been asked to give 15-minute talks, and they've all agreed. Right here shows what day 1 and day 2 of these look like. If you're interested, I would hope that you go register. It's free. I think last I checked, it's over 800 people already registered for this thing. So short talks, couple hours for 2 days. You tune in when you want. It should be really great. And I will end it there. Thank you for your time, and I hope you enjoy the rest of the session.